Hi, I'm Silvia, application engineer with MCAD Engineering, and I'm here today to talk about our stand tool, a unique and patented solution for the stability analysis of RF and microwave circuits. The stability analysis is a key step in the design flow of RF and microwave circuits. If we look at power amplifiers, to achieve maximum power efficiency, they work near the saturation region, risking the presence of nonlinear distortion. In addition, because of the configuration with feedback loops, power amplifiers often present oscillations at the frequency division by 2, or hysteresis. There are different methodologies for the stability analysis of RF and microwave circuits, such as the well-known Rowley factor, already implemented in most commercial simulators. However, this analysis is only valid for a linear two-port network, intrinsically stable, and for a fixed bias point. It is not valid for the analysis of multi-stage power amplifiers with multiple active devices and feedback loops, where the internal stability fulfillment is more difficult to ensure. But STAM proposes a much more powerful approach, where stability analysis in both linear and nonlinear conditions can be performed in a rigorous, fast, and intuitive manner. Thanks to its parametric multi-node and Monte Carlo analysis, just by taking a look at the pole zero map provided by a STAM tool, the designer will have the necessary information about the dynamics of the circuit to apply stabilization techniques with the least consequences for the circuit performances. In the following, the stability analysis using a STAM tool will be illustrated using Cadence AWR. The stability analysis using a STAM tool is integrated in the Cadence AWR simulator through the STAM wizard. But first, we need to run the software IBCAD where we find a STAM tool and check out the parameters for the communication between the two platforms. Once the configuration in IBCAD is ready, we go back to AWR. Here, we have already implemented the design example of an amplifier. This is a 35 dBm amplifier working at 4 GHz that uses an MCAD GaN transistor compact model that considers traps and thermal effects. Looking at the transistor, we see that the transistor model is blocked. Using a STAM tool, the user does not need to access the transistor model to check the stability. The first things the user needs to do in AWR is to add a stability probe to a sensitive node of the amplifier. To do so, we do Ctrl-L, we search for the stab probe, and we connect it to the gate node of the transistor. For more information about the best nodes to connect the stability probe, please take a look at our application note selecting the circuit node with STAM, available in our website. Now we are ready to set up the stability analysis. We go and open the wizard stability analysis using STAM. On the first page, we select the circuit schematic for the analysis. Then, clicking on Next, we see that the wizard has detected our stability probe. And in the simulation settings, we are going to set up the parameters that STAM needs for the identification. The first parameters are associated with the identification techniques used by a STAM tool to obtain the pole zero map. The order of the identification function can be set automatically through the automatic algorithm implemented in STAM, where the algorithm will fit the frequency response of the circuit through a number of iterations trying to keep the phase error under a phase tolerance value. So here, looking at the parameters, the phase tolerance is the maximum error permitted in the automatic algorithm. Note that a phase tolerance too small may give rise to numerical errors, so 0.5 degrees will be used in this case. In small signal test conditions, the user will set up the frequency band for the analysis. Here we will perform a linear stability analysis to illustrate the use of STAM tool, so a frequency band that considers the whole operation band of the active device may be defined. Be careful with the number of frequency points. The frequency response should be well sampled. The type of stability analysis will be defined in the drive conditions. In analysis type, we select linear, and the value of p-start will not be taken into account for linear analysis. Finally, before launching the identification, we check out that the stand wizard settings are the same as in IVCAD, clicking on Show Secondary. After clicking on Finish, AWR will simulate to obtain the frequency response of the design and then send it to a stand to be identified. So now that the simulation has finished, a new graph has been created. This graph is the pole zero map of the design, and a circuit will be unstable if there are poles with a positive real part, and the presence of complex conjugate poles means that an oscillation will start up at the frequency of the poles. The frequency of poles and zeros is given by their imaginary part. So here in this example we can see that the circuit is unstable and the instabilities are at 386 MHz, 3.4 GHz and 3.8 GHz. This pole zero graph has been created automatically by AWR, but all the stand data is available in the stand library. So if we go to Add Measurements, Nonlinear, and we select Stability, we see the stand poles and zeros as well as the simulated frequency response, stand data, and the transfer function obtained by stand to create the pole zero map, stand approx. Looking at these functions allow the user to be sure that the frequency response is well sampled and that there is a good fitting between the two of them. During this short video, we gave a quick overview on how to use the stand wizard in AWR for the stability analysis of RF power amplifiers. Many other stability analyses are available in a stand tool, such as nonlinear stability analysis, parametric, or Monte Carlo analysis. Please do not hesitate to contact us if you want to learn more about a stand tool, a unique solution for the stability analysis of RF and microwave circuits. Thank you.